So welcome to the class on EE540 Advanced Electromagnetic Theory and Antennas. I am Professor Rakesh Singh Kshatriya. So in this class we'll discuss about the Hertz dipole. Hertz dipole is the basic building block for any kind of antennas. So this is the most fundamental antenna we'll be discussing. So by the way, what is this Hertz dipole? Hertz dipole is basically a small current carrying element, infinitesimally small, of length dl. And the procedure for finding the fields produced by this Hertz dipole is you first know the current density, and from the current density you find the magnetic vector potential. Then from the magnetic vector potential you find the magnetic field, and finally you find the electric field. So that is the process we are going to follow. So now this infinitesimally small current carrying element is carrying a current, and you know that in order to have radiation we should have a time varying current, a current which is changing with time. So the time varying current we are considering now is expressed as I0 exponential j omega t, and we assume that the pole is positioned along the z-axis, so current is flowing along the z-axis. So direction of current flow is along the positive z-axis, amplitude is I0, and variation with respect to time is given by exponential ij omega t. Omega is the angular frequency of the current. And as you know that magnetic vector potential follows the direction of the current, so magnetic vector potential will also have only z component. So the A vector will have z component az directed along the z hat, and you can easily find out what is the expression for the magnetic vector potential once you know the current. We'll derive this in the next slide. So the first thing is that in the expression you have for magnetic vector potential, which is a convolution of Green's function with the minus mu j r dash, and this is the final expression you have for the magnetic vector potential. It's very well known and most of you must be knowing. But now what we are going to do is we'll consider case for the Hertz dipole, which is an infinitesimally small current carrying element. What was the amplitude of the current? I naught. Time variation was exponential j omega t. What is the length? The length is dl, so the j r dash dv dash will be replaced by I naught dl exponential j omega t. For the infinitesimally small current carrying element, the size of the antenna is infinitesimally small and its position at the origin. So in that case r minus r dash will simply become r dash is very small. We are positioning the dipole in the origin, so this term will become 0. We just have r is equal minus r dash is equal to r hat, r vector, just the r vector minus r dash will become r vector only, because we are positioning the dipole in the origin and its dimension is negligible. So in that case the expression for the magnetic vector potential az z hat will become simply mu. From here j will be replaced by I naught exponential minus j beta r, and dv dash will become dl, and r minus r dash will become r, so exponential minus j beta r by 4 pi r. So this is the expression you have for the magnetic vector potential for a Hertz dipole. So this diagram will show the location of the Hertz dipole. It's at the origin. It's a small current carrying element of length dl, and current is time varying and amplitude is I naught. Variation with respect to time is exponential j omega t. Now we are observing this field produced by this small current carrying element at this point P, and we'll consider the spherical coordinate system, and the spherical coordinate system will have r theta and phi, and these are the direction for the r theta and phi unit vectors. Since the dipole, Hertz dipole, the current is flowing along the z-axis and its position along the z-axis, the magnetic vector potential will also have only z component. But then we are interested in finding the fields in the spherical coordinate system. But what we have here is magnetic vector potential is having a z component. So I need to do some kind of coordinate transformation so that I can transfer from the Cartesian coordinates to the spherical coordinates. So this is the relation between the spherical coordinates, a vector in spherical coordinates ar, a theta, a phi. Let's say this is the magnetic vector potential in the spherical coordinate system. You can obtain it from the magnetic vector potential in the Cartesian coordinate system, ax, ay, az, by multiplying with this coordinate transformation matrix. So now here in this case we have a major simplification because magnetic vector potential is having only z component az here. So when you multiply it, you will only get ar. Ar is basically az cos theta. Ay, a theta is minus sin theta az, and fi will be 0. You can look from this here, fi will be 0 because when you multiply this with this, you are getting 0. So from this diagram also, without doing any coordinate transformation also, you can simply find out what is ar and a theta. Az direction is along this direction, r is along this, theta is along this. So if I want to find projection of az along the radial direction, that would be az cos theta. This angle is theta, so that's what we are getting here, az cos theta. If I want to find the projection of az along the theta direction, then I should find az cos theta plus pi by 2. You know that the angle between the radial unit vector and theta unit vector is pi by 2. This angle is theta, so the total angle is theta plus pi by 2. So az cos theta plus pi by 2 is simply minus az sin theta. So without doing coordinate transformation also, you can find out the relation between ar, a theta and a phi for this simple case. So the first step is, once I have magnetic vector potential, I want to find magnetic field. You can use Maxwell curl equation. So magnetic vector potential, you take the curl of that, divide by mu naught, you should be getting the magnetic field. And the curl we are taking now will be in the spherical coordinate system. In the spherical coordinate system, this is basically 1 by product of all scale factors in the spherical coordinate system, 1 by mu naught. What are the scale factors for spherical coordinate system? R1, r sin theta. When you multiply all of them, you get r square sin theta. Then you have r hat, scale factor 1 r hat, scale factor 2 theta hat, scale factor 3 phi hat. So scale factor 1 is 1, scale factor 2 is r, scale factor 3 is r sin theta. That's what you have, 1 r sin theta. So you multiply by 1 here, you multiply by r here, and you multiply by r sin theta here, and there's the partial derivative with respect to r, theta and phi. Even for the ar, a theta and a phi component, you multiply by 1 r sin theta. So that's how you find the curl in the spherical coordinate system. And you also see that your fill will have no variation along phi, because your Hertz dipole was directed along the z-axis, so there should not be any variation of field with respect to phi. So let us find out the magnetic field. So here, since the field is not varying with respect to phi, dou by dou phi will become 0, a major simplification, and we just have AR and A theta. AR was AZ cos theta, A theta was AZ sin theta with a negative sign. You are multiplying by R here, so AZ cos theta minus R AZ sin theta. So this is a simple expression, you can find it out. So when you find out, what you will be seeing is that H R is 0, H theta is 0, only H phi has a value here, finite value you have here. So finally you differentiate it, this expression you can find out, and you can express the H phi is simply phi hat I naught dl exponential plus j omega t exponential minus j beta r sin theta by 4 pi j beta by r plus 1 by r square. So now the first observation is that the Hertz dipole has only phi component to the magnetic field. That is because current was flowing in the z direction, and magnetic field circulates the current. You can apply right hand rule and see how is the magnetic field for a current flowing along the z axis. Another observation is that the magnetic field has a variation with respect to r as 1 by r and 1 by r square. So in the previous class, what were the two conditions for a source to have electromagnetic waves? The first condition was it should have a field, magnetic field or electric field, along the direction which is perpendicular to the radial directions. So here your magnetic field is perpendicular to the radial direction. It has only phi component, and you also clearly see that, so magnetic field has only phi component, and you also clearly see that we have a term which is dependent with respect to r as 1 by r. So this will give me radiated waves which should be able to reach out to far away distance. So it has a phi component and it has a variation with respect to r as 1 by r. So now we can find electric field from the magnetic field usually by using the Maxwell curl equation. You take the curl of the magnetic field divided by j omega epsilon, you should be able to find the electric field. As usual, like before, here we also know that due to the symmetry there will not be any field variation along the phi direction, so this d by d phi will become 0, and magnetic field has only phi component, so the only last term will be non-zero. So we multiply by scale factor 1 r sin theta, so r sin theta is phi component of the magnetic field. Then you can find out electric field. What we'll observe is that electric field here has component along radial direction and theta direction. So radial direction component is like this, and theta component is like this. So here you can see that this r and r cancel out. What you have is r square and r cube term. So this radial direction component of the electric field has variation with respect to r as 1 by r square and 1 by r to the power cube. So this kind of field won't be able to reach for far distance. It will not be giving me any kind of electromagnetic waves. in the far field. But let us look at the theta component. It has a component which is varying as 1 by r, 1 by r square, and 1 by r cube. So since we have 1 by r term here, this field will be giving me far fields, and its direction is along the theta direction, so it is perpendicular to the radial direction. So one observation is that electric field has r and theta component, magnetic field has phi component. They are perpendicular to each other. So now, depending on the variation of the fields with respect to r, 1 by r, 1 by r square, and 1 by r cube, we can differentiate different kinds of field. Fields which are varying with respect to 1 by r can be called as radiation fields. Fields which are varying with respect to r as 1 by r square can be called as induction fields. And finally, the fields which are varying with respect to 1 by r cube is called the electrostatic fields. And one more close observation is that fields which are varying with respect to 1 by r cube is inversely proportional to omega. That means as we go for higher and higher frequency, these fields will become more and more smaller. That means electrostatic fields are becoming smaller and smaller when we go for a higher frequency. Let us look at the induction field expression, and from the induction field expression what we are getting is beta by omega. So beta, what is beta? Beta is omega is square root of mu epsilon. So omega here and omega here will cancel out. So that means induction fields are independent of frequency. How about the radiation field? In the radiation field term, you are observing that we have a term like beta squared by omega. So beta squared by omega means omega square mu epsilon. So omega here and omega square here cancels out, and we get omega in the numerator. So that means basically your radiation fields are directly proportional to frequency. That means when you go for higher and higher frequency, radiation fields will become more and more dominant. So let us look at the fields. One field, we'll call it near fields, which are existing near the dipole antenna, Hertz dipole antenna, and they will have a variation with respect to r as 1 by r square and 1 by r cube. So these are the near field for the Hertz dipole. This is the magnetic field, and this is the electric field. Will have both E theta and E r component. Magnetic field will have only phi component. So the expression, if you look closely for the magnetic field, it's very similar to the Biot-Sievert's law. And if you look at the near field component for the electric field produced by a Hertz dipole, and it looks like electric fields produced by an electric dipole. This is the radial component, and this is the theta component. And as you know that pointing vector, when you find out pointing vector will be instantaneous pointing vector is E cross I c star. E is the electric field, I c is the magnetic field, star means complex conjugate. When you do that, cross product of electric field and magnetic field will have terms for the near field as pointing vector varying as 1 by r to the power 5 and 1 by r to the power 4. So obviously this kind of fields will die out pretty soon after some distance. But the fields which are called far fields will have variation with respect to r as 1 by r. This is a far field for the Hertz dipole, the phi component of the magnetic field, and this is the theta component of the electric field. FF here means far field. We have a field variation with respect to r as 1 by r here also. So when I do cross product of electric field and magnetic field in the far field, I'm getting pointing vector as of the term 1 by r square. So pointing vector is power density. You consider a giant sphere enclosing this source at a very far away distance. You find out the area of the sphere. Sphere area is 4 pi r square, and pointing vector is varying as 1 by r square. So when you multiply these two, you get the total radiated power at any arbitrary distance from the source in the far field, and what you're getting is 4 pi, which is a constant. What does this mean? This means that you find out the total radiated power from the source at any location in the far field. R can be anything. You are getting a constant power. So power is constant, energy is conserved. So when the wave is moving from one distance to another distance in the far field, there is no change in the energy. So in that case, the fields which are produced by the Hertz dipole would be able to reach out infinite distance, because power is conserved, energy is conserved, is not changing when it moves from one place to another place in the far field. So that's a signature for the electromagnetic waves, an irreversible flow of energy from the source to the far away distance. So the minimum bare necessity for electromagnetic waves are satisfied by these far fields from the Hertz dipole. One is that it has E theta and H pi components which are perpendicular or radial to the direction of power flow. Pointing vector is along the radial direction, because when you do cross product of E theta and H phi, that will be vectors should be perpendicular to both E theta and E phi, that is E theta and H phi, that is radial direction. In other words, we have transversal fields for the Hertz dipole, which is supplied with a time-varying current. And one more observation is that the fields vary as 1 by r for the far field, for the radiation fields. So this is the signature for electromagnetic waves, is satisfied by the fields produced by a time-varying current supplied to a infinitesimally small current carrying element, also called as Hertz dipole. We can also observe that there are three types of field, and what you can observe is these three types of fields are equal at a distance. We can find out that this is the component which are dependent on 1 by r, these are components which are dependent on 1 by r square, and this is the component which is dependent on 1 by r cube. When you equate this three fields which are varying as 1 by r, 1 by r square and 1 by r cube, you will find that r is 1 by beta, which is basically lambda by 2 pi. So at a distance of r is equal to lambda by 2 pi, you will have all the fields equal. And one more thing is that r, if it is less than lambda by 2 pi, then electrostatic fields will dominate. In that case, 1 by r cube term will have maximum value. When r is very much greater than lambda by 2 pi, the radiated fields will dominate. That means fields which are varying as 1 by r will dominate. So near field result is when r is very much less than lambda by 2 pi. Electrostatic fields dominate. You can find out the approximate value of the electric field when r is very much lesser than lambda by 2 pi. When r is a very small number, exponential minus j beta r will also tend to 0. this r will tend to 0, so exponential minus j beta r will tend to 1. So we can simplify the expression for the electric field approximate value of er and e theta with the components 1 by r cube. So this er has a variation with respect to theta as cos theta, e theta has a variation with respect to theta as sin theta. If I want to find the magnitude of the near field, then I should take square root of er square plus e theta square. In that case, other terms are same except the dependence with respect to theta. First is er is dependent with respect to theta as cosine of theta, and e theta is with respect to dependent with respect to theta is sin theta. So the modulus for electric field will have a term 4 cosine square theta plus sin square theta. So if I am interested in plotting the electric field with respect to variables r theta and phi, then the dependence with respect to theta will be from this term here. So that is basically your field pattern, no? So look at this expression, f of theta is square root of 4 cosine square theta plus sin square theta. This will give me the field variation with respect to theta. So looking at this term, it will have a maximum field for theta is equal to 0. Theta is equal to 0, sine will become 0, this will become 1. So you'll have maximum value when theta is equal to 0 or even theta is equal to pi. And you'll have a minimum value when theta is equal to pi by 2. When theta is equal to pi by 2, this term will become 1, this term will become 0. Or theta is equal to 3 pi by 2. So this is the plot of the electric field radiation pattern for the Hertz dipole in the near field. So you observe that at theta is equal to 0 and pi, there is a maximum radiation. There is no radiation or very small radiation along the theta is equal to pi by 2 and 3 pi by 2. So the distance from this point to this will give me the amplitude of the field along that direction. Similarly, distance of this point to this point will give me how much is the electric field radiated in along that direction. You can see that this is longer, this is shorter, so obviously we'll have more radiation along theta is equal to 0 and 180 degree. Less radiation along theta is equal to 90 degree and 270 degree. So, but most of the time we are interested in the far field region. This is the fields we will be using for wireless communication. Let's say you use mobile phones, you have mobile communications, signals from the mobile phones go to the base station and it comes from the base station to the mobile phone. So those kind of communication basically requires far field region of they actually operate in the far field region of the antenna, and we are considering the case when r is very much greater than lambda by 2 pi. In that case, if r is very much greater than lambda by 2 pi, kr will also become very large and it will be much greater than 1. And we have only e theta and I phi component for the far fields, and this is the expression we have derived for the electric field and magnetic field in the far field. One point to be observed is that their variation with respect to r is 1 by r. Here also it's 1 by r, and the variation with respect to theta is sin theta here, also sin theta here. And look at this term here, you have a j here. So j will give me a phase shift of pi by 2. Here also j will give me a phase shift of pi by 2. So electric fields and magnetic fields are in phase with each other and 90 degree out of phase with the current due to the j term in the expression for E theta and I phi. And you can also take the ratio of E theta and I phi, and it turns out to be beta by omega epsilon. You can simplify it. It's basically square root by mu by epsilon. So the ratio of the electric field and far field and magnetic field in the far field is equal to the eta. Eta is a wave impedance for the medium. So if we have free space, eta will become 377 ohm. So electric field is a larger quantity, magnetic field is a smaller quantity. And one more observation is that the variation of your electric field and magnetic field with respect to theta was sine theta. So sine theta is 0 when theta is equal to 0, and sine theta is maximum when theta is equal to pi by 2. So how does the radiation pattern look like? The radiation pattern looks like 8 maximum radiation along the theta is equal to pi by 2 and 3 pi by 2. No radiation along the theta is equal to 0 and 180 degree. So this radiation pattern is different from the near field radiation pattern, so don't get confused. You may have a different radiation pattern in the near field. You may also have a completely different radiation in the far field. That is because your electric field and magnetic field will have different expression in the near field and far field. So antenna will have different radiation patterns in near field and far field. Let us look at the power flow. The power flow is basically given by the Poynting vector S vector. We are interested in the average power flow, so then we find the S average, which basically have real part of E cross H star. Electric field has radial component and theta component. Magnetic field has only phi component. So the average power flow would be like this in the far field. So what observation we can make is the average power flow is radial in direction, and the power density is varying with respect to theta, so it's not same. You have sine square theta term here. Because of that, power density is not same in all directions. And the net real power flow is due to the far field components, radiation fields only. Near field components are not contributing here. So now once you have the average S average, which is the power flow per unit area, if I want to find the total radiated power from a Hertz dipole, I just integrate it. And we'll be doing integration in the spherical coordinate system. How do we do integration in the spherical coordinate system? I just find out scale factor 1 dr. So basically what we are doing is surface integration. Now the Poynting vector is directed along the radial direction, so obviously the surface element we'll be considering will be in the theta and phi plane, because its direction is along the radial direction. We'll have surface element in theta and phi plane. What is the scale factor for theta and phi? Scale factor for theta is r, for phi is r sine theta. So what we do is we find scale factor 2 d theta, scale factor 3 d phi. So scale factor 2 is r, scale factor 3 is r sine theta, so r square sine theta d phi. So we have the power density S average. You just multiply by r square sine theta d phi to the integration over d theta and d phi. And finally the expression for the total radiated power from a Hertz dipole is simply 40 pi square I naught square dl by lambda whole square. So these are almost constant. The only variation is with respect to this. Let us try to interpret this expression you have for the total radiated power from a Hertz dipole. First thing is that total radiated power is directly proportional to the square of the dipole length. So if you increase the size of the dipole, the power radiated will be increasing, because we have dl square term in the numerator. So Larger is the size of the antenna, the more is the power radiated from the antenna. Our Hertz dipole was a small current carrying element. The power radiated from this Hertz dipole is very small. Second thing is that the power radiated is inversely proportional to the dipole wavelength. We have a lambda in the denominator here, lambda square. So that means for smaller and smaller lambda, we should be having more total radiated power. So smaller lambda means higher frequency. If you go for higher and higher frequency, the total radiated power will become higher and higher. If you go for larger and larger size of the antenna, total radiated power will be larger. So it means that the power radiated will be more and more for higher frequency and larger size of the antenna. You can even find the radiation resistance of Hertz dipole. So if you want to find the radiation resistance of Hertz dipole, you equate the total radiated power to half I naught square R radiation. So from here you can find out how much is the radiation resistance of the Hertz dipole. So you can actually equivalently model a Hertz dipole by a simple resistor of value radiation resistance. Radiation resistance is 80 pi square dl by lambda whole square. So a simple model of Hertz dipole is a radiation resistance R radiation, which is of value 80 pi square dl by lambda whole square. You can also draw the radiation pattern of Hertz dipole, and you know that variation with respect to theta was sine theta. And the 3D radiation pattern looks like apple. You have less radiation along this, more radiation along this. So now plotting a 3D radiation pattern on a 2D plane is a very difficult task. I have done this plot for the radiation pattern, 3D radiation pattern of a Hertz dipole using MATLAB. Let us say you want to draw this radiation pattern with hand, pen and pencil on a paper on a page. You want to draw it. So paper is a 2D plane and you want to draw a 3D radiation pattern. That is going to be very tough. So now there's a cure for this. You can simply cut this apple into two planes. One is called E plane, another is H plane, and they are called the principal planes of the antenna, and just find out the fields in the two principal planes. So conventionally we usually find the field patterns of the antenna in two planes. One is the E plane, another is the H plane. E plane is the vertical cut and H plane is the horizontal cut. So now once you have this E plane and H plane pattern, we are interested in, let's say, 3D pattern. You can achieve it. For example, in this case for Hertz dipole, the H plane pattern looks like a circle. That means along the phi direction there is no change in the field variation. Field is constant, so it's almost like a circle. But along the theta direction, field is maximum along theta is equal to 90 degree and 270 degree, and we don't have any field radiation along theta is equal to 0 degree. So this is the E plane pattern and this is the H plane pattern. Once you have these two principal plane patterns of the antenna, you can easily generate the 3D pattern. For example, you rotate this E plane in a circle, then you will be getting the radiation pattern you have for the Hertz dipole. And this distance shows the how much is the maximum radiated field along that direction. So if you want to get the 3D plane, you just need to rotate the E plane pattern along the H plane pattern. So in this case, it will give me the shape of an apple. And people usually call theta as elevation angle, phi as azimuthal angles. And sometimes E-plane pattern is also called as elevation patterns, and H-plane pattern is also called as azimuthal pattern. Why? Because you see, what we are actually observing here is that what is the variation of the fields with respect to phi. Phi is the azimuthal angle, so we call it, this is azimuthal angle pattern. Here we are observing how is the field variation with respect to theta. Theta is the elevation angle, so we call it elevation pattern. So E-plane pattern is also called for dipole antenna as elevation pattern, and H-plane pattern is also called as azimuthal pattern. So now in this class we have actually characterized Hertz dipole, which is the fundamental basic building block for any antenna, completely. We find the fields, we find the patterns, we find the total radiated power, we also find the equivalent circuit. That's all for this class. Thank you.